Hi guys, welcome to the last tutorial of our embedded systems course, tutorial 10. We will discuss the automotive RTES. We will start with something called ECU. What's an ECU? It's an electronic control unit, which is an embedded system, okay, in automotive electronics that controls one or more electronic system in a vehicle. Meaning that all the components that you have in your car, your lights, your windshield, your air conditioning, all of these things are not connected to one ECU. So each group of these electronic components, it's actually connected to one ECU, and these ECUs are connected together. So let's say we have like sensors now and actuators. Let's talk about the sensor, parking sensor we have in the car, not in the project, in the car, in the actual car. This sensor detects the spaces and sends an alert for the driver not to crash in anything while parking. So the thing is that the sensor measures the distance and decodes the measuring itself in some way and transmit it to the corresponding ECU. So what we are going to do now is to understand how to encode these readings into values that our ECU understands and easy to be transmitted from the sensor to our or its corresponding ECU. Okay, the sensor reads something. We need these something to be readable by the ECU. So these signals, we will start with understanding how to convert its reading range into number of bits, into whether our data is signed or unsigned, and so on and so forth. So question 1, we have something called an electronic throttle control. This is something in cars. Okay, we will read the description and then say it in a simpler manner. Okay, an electronic throttle control is an automobile technology which electronically connects the accelerator pedal to the throttle, replacing a mechanical linkage. A typical ETC system consists of 3 major components: an accelerator pedal module, a throttle valve that can be opened and closed, and last but not least, an engine control module. We are interested in the characteristics of the signal linked to the degree of opening of the throttle. The angle varies from negative 180 degrees to positive 180 degrees with steps of 0.5, which is our resolution or the signal resolution. So now you are driving, you have a car and you're going to campus. So the road is clear, so you push your gas pedal to the maximum, so you have more speed, more acceleration, right? But you have something appears out of nowhere while driving at maximum speed. You take your leg off the pedal and your car starts to decelerate. So what had happened here? When you push your pedal to the maximum in your car, you are allowing more air to go into the motor, so it burns your gas, so it accelerates the car. And when you take it off, gradually, suddenly, you allow less air to go into the motor, so your car decelerates. So this is the linkage between your, let's say, the force you put on the pedal that you see and the motor inside, the amount of air which enters the motor. This is the linkage between both. So the force that you put on the pedal is, let's say, converted via that throttle, which has an opening angle of negative 180 to positive 180. Okay, with resolution of 0.1, meaning that we go 0.1, 0.2, 0.3, 0.4, 20.1, 20. So on and so forth. Okay, so the throttle is the linkage, literally linkage between the force that you put on the pedal and the motor and the amount of air which enters the pedal. Maybe I'm not entirely correct, but this is the simplest explanation of what a throttle is. Okay, now we were going to answer the question. Question one here. It says how many values should be coded. So we will get back to our information on the range, on the angle range, which varies from negative 180 to positive 180 with resolution of 0.1 or step size of 0.1. So we have, as we can say, we have values in the negative from negative 180 and values in the positive 180, right? And the value of 0 in the middle. And we have a step size of 0.1. So the total values which should be coded are the following. We will add up all these values together. We'll add the 180 in the negative spectrum plus the 180 in the positive spectrum, right? And then we were going to multiply them by 10, which is the step size I mentioned before. Why 10? Because 0.1 represents that we have a step of 0.1, meaning that if we want to step from 1 to 2, we will have to go 1.0, 1.1, 1.2, 1.3 up until 1.9. So if we count these values, we will have 10. So between each whole value and the other, we have a range of 10. So it's not just 180, 180. No, we don't have a step of a whole number. We have a step of 0.1. That's why we have a multiplication by 10. We will add the 1 of the 0 because we did not include it. Okay, because it's a whole value. So adding all of these up together, we will have the values to be coded are 3601. This is the total number of values to be coded. Okay, we need to remember that the values that we get from the throttle is analog, right? And whatever we have is going to be decoded in digital, right? Okay, that's a side note. So the total number of values is 3601. So going to the next question, it says how many bits, number of bits necessary to represent the range that we just calculated, which was 3601. So simply we will use the log base 2, 3601. This will be equal to 11.8 bits. And we don't have such things, so we will just do an approximation. So we will have 12, why it's just like that. We will have 12 bits. Let me just write it in a better way. Yeah, because it's too ugly. Yeah, so it's 12 bits. Okay, so we have 12 bits to represent the 3601, but actually we will be having more values than needed, okay, because we did the approximation. Moving on to the next question, It says, what should be the signal type? Okay, as mentioned earlier, we have values in the negative spectrum and the positive spectrum. So this value should be signed value, right? It should be signed. The signal type should be signed because we receive negative values and positive values. Okay? Okay, next, what are the maximum and minimum brood values of the signal? Okay, the brood values is the total values based on the number of bits that we just had. The number of bits that we have is 12 bits, right? We have 12 bits. So we will have minimum value. Our minimum value is negative 2 power 12 minus 1, which is equal to let me check it. Okay, which is equal to negative 2048. This is the minimum value. Okay, and the positive value, positive 2 power 10 minus 1 minus 1, which will be equal to 2047 maximum. Okay, this is the maximum value and the minimum values of this specific signal. Okay, moving on to the next question. It says, what is the factor and the offset? Okay, offset meaning that we will skip some values and we start at a certain offset, a certain place. We don't have that, but we have a factor. The factor is the resolution, which is the 0.1. So our factor is the resolution, which is 0.1, right? And the offset here is non-existent. We have no offset because we consider the whole range. Okay, so the factor is the resolution, which is 0.1, and we don't have any offset because we consider all the range. Okay. Okay, getting now to the actual the last question, which is, it says, what are the maximum and the minimum values of the signal? Okay, so now the maximum and the minimum values of the signal, we said that the broad values, or the actual values, are negative 2048. This is the minimum value, and positive 20. Sorry. Yeah. 47 is the maximum value, right? Okay, cool. Now we want to know the maximum and the minimum values of the signal, which we'll be getting. Okay, in this question, as we mentioned before, again, it says, what are the maximum and minimum values of the signal? From question D, we already calculated the values in the minimum range and in the positive range and in the negative range, the total values. But what values would I be reading? The question number D just saying that in the negative spectrum we will be having 2 plus k values and 2 plus k in the positive spectrum. So okay, that's cool, but what about the actual values that the signal will be given? So going to our question, we know that we have negative 2048 in the minimum what in the negative spectrum, and positive 2047 in the positive spectrum. So we need to know the range of the actual values that we will be having. So so what we will be having, which we will simply, okay, in the negative spectrum we will be having negative 2048 times our resolution, which is 0.1. Now what we are doing again, sorry if I got it mixed up, question number D, we calculated the total number in the positive and the negative spectrum, the minimum value and the maximum value. Okay, meaning that the minimum values is negative 2048 and up to positive 2047 in the positive spectrum. Okay, so okay, good. Now we want to know the actual value that we will be reading. Okay, so we will multiply each range by our resolution, which is 0.1. So here, if we multiply this by 0.1, we will have negative 204.8. This is the minimum value, and in the positive value is 2047 times 0.1 equal positive 204.7. So this is the maximum value. I should be writing it in a better way. So the answer of this question, so the maximum value of this signal is 204.7, and the minimum value is negative 204.8. Okay, cool. Going to the next question. The next question is a bit, it's the same as question 1, but it's in a shorter manner. Okay, in this exercise you will be setting up the characteristics of the following signals. We have 3 signals: running engine, signal information if the engine is running or not. The second one is vehicle speed, and the precision is 0.1 kilometer per hour. For a mid-range sedan car, what should be a maximum speed? We will talk about this now. And last but not least, the oil temperature, precision of 2 degrees Celsius, values from negative 50 degrees to positive 150 degrees. So in order to do so, complete the following table. Please note that you will only be using the unsigned type. So our signals, our 3 signals are, you can say that they are unsigned, so we will not care about the signal type. We will just care about the what you can say, the actual values. Okay, so our physical value, which comes out of our signal, is as the following. Okay, we will start the engine running. The information given is signal information, signal informing if the engine is running or not. So it's black or white, right? This or that, right? Right. So when we come here to complete this table, our physical value, which comes out of the electronic device, is the following. Okay, the minimum value of the signal is 0, which corresponds to the engine is not running, right? The maximum value is 1, right? It's running. It's either running or not. We don't have any kind of other values. We don't have resolution. Do we have resolution here? Yeah, we do have resolution, because we have a step size either 0 or 1, right? So our resolution is 1. Again, it's not mentioned here, but we can infer from this, as our maximum value is 1 and the minimum value is 0, and the signal itself, what does it do? It just says it's on, it's off. We don't have 0.5, we just have from 0 it's off, 1 it's on. Our resolution is 1, a step size of 1. Okay. Come to the digital value part. Okay, then the total number of values we have is the total values that we could read. How many values we could read? We could read 0 or we could read 1, right? 0, 1, so it's 2 values, 1 and 2, right? Okay, to represent the 2, we need how many bits to represent this range? How many bits we need? We go and do log 2 base 2 is equal to 1, so it is 1. Okay, good. The type is it's unsigned. It's all going to be unsigned. Okay, do we have an offset? Nope, we don't have an offset, right? We will, it is 0 or 1, nothing special about this. And the last but not least, which is the factor, is the resolution, but it's in disguise, so act as if we did not answer it before. So the resolution is 1. Woo, yay, it's 1. So again, the engine running, the signal informing if the engine is running or not. So it's black or white. We don't have like the throttle 0.1, 0.2, no, we don't have resolution. We don't have float resolution, okay, because it's we have a whole number resolution, even if it's not mentioned. Okay, so either it's black, it's not working, or it is working, it's 1. The resolution is 1 because we have a step size of 1, and this is the physical values from the information given. Okay, good. The digital value, which will be decoded later on, we are informing the ECU that this signal has total of 2 values, 0 or 1, it's 1, 2. We count them 1 or 2. We don't look at their actual value, we count them. So here we count our total range of values, so we have 2, just that. The number of bits, we will calculate it from the log 2, log base 2 is 1. And as mentioned before in the question, that the type is unsigned for all the signals. So moving on to the offset, it did not mention that we will skip something and start from that place, so its offset is 0. And the factor, again, it's disguised as resolution. It's resolution in the physical value, and it's a factor in the digital value. So this change of names because we change our, let's say, our medium. Okay, so the second one is the following. The vehicle speed, precision of 0.1. Yeah, I can see you there. Yeah, it's the resolution and the factor. Same. For a mid-range sedan car, what would be the maximum speed? Okay, now we are calculating the vehicle speed, right? Okay. Our minimum value is, you can have 0 speed, right? You're not moving, so you could have 0 speed because the car is not moving. So the maximum speed, the doctor said that we will be having a maximum, the maximum value of the physical value of 300. Okay, it's really super car for a mid-range sedan car. Okay, cool. We will just stick with the 300. Okay, and then our resolution, as it says, it's 0.1. That's cool. Okay, so the physical value, we get the information from the information given. So coming to the digital value, we just like write this in a fancier way. So the total number of values is 300 plus 0, right? So we can have 0, 0.1, 0.2, 0, like that. So we have, sorry. We have 300 times, as we calculated in the previous question, 0.1, which is going to be, not 0.1, 10, sorry. So it's going to be 3,000, right? 3,000, yeah, right? And we will add the 1 for the 0, so it's going to be 3,001. So the total values that we is going to have is 3,001. Cool? Okay. And the total number of bits, log base 2, 301. This is going to be, I guess, 12. If not, this means that we did the what you could say, we did the approximation, so it's 12 bits. Cool. Mentioned before, what type is unsigned? Thank you for answering. So the next thing, do we have any kind of offset? No. So it is 0. We don't skip any values. And the factor, okay, it's 0.1. Yeah. Okay. So the vehicle speed, the minimum value 0. You can have 0 value up to 300. We will stick to the answer of this question, to 300. You can make it whatever. You can make it 120. You can make it whatever. But the vehicle speed can actually have a maximum of 320 or more. So we will just compromise and say it's 300. And our resolution is 0.1 kilometer per hour. And this is the physical values of this signal. We want to know how to decode it into a digital value, so we get to calculate the total number of values by having the maximum value multiplied by our resolution, which is by 10, because between each two whole numbers, our two whole values, we have 10 steps. Okay, and we add the 0. Okay, So we have 3K1 total values, and then we use the log base 2 301 to get the number of bits. Sometimes it's not a whole number, so we go to ceiling, not flooring, because it's okay to have more bits, not in the all cases, but it's better to have more bits than fewer bits than actually needed. So the signal would be read or be presented fully. Okay, and then the type, it's already decided for us. It is unsigned, and our offset, it did not mention that we are starting in a different place in our range, this range. No, it didn't say anything. So our offset is 0, and the factor, as we said, it's the fancier word of the resolution in the digital value, which is the factor. Okay, cool. Next, the last one is the oil temperature. So the oil temperature has a precision of 2 degrees Celsius, values from negative 50 degrees to 150 degrees. Perfect. So we will go and fill the last part of our table. The oil temperature starts, the minimum value starts from negative 50. The maximum value is 150. Our resolution is 2 degrees, right? Perfect. That's good. Okay, cool. So now the total number of values that we will be having, we will add the negative 50 and the 50 plus 1, which is the 0. We have 50 here plus 150 and plus 1, which corresponds to the 0. So we will be having 101 values. Okay. Okay. Which we have here 101, and the total number of bits log base 2 101, which is 7. If it's not 7, so we got it compromised. Approximation, we had the approximation, so number of bits is 7. Again, the type is unsigned, we know that. And do we have here an offset or not? That's the question. But let me go to the factor. We have a factor of 2, which is the resolution, right? Right, cool. Okay. The oil temperature, precision of 2 degrees Celsius, values from negative 50 degrees to 150 degrees. Okay. Okay, the total number of values, we will add the minimum. We are calculating this now again. I just calculated it very fast, and I did not explain it. I will explain it now again. Okay, cool. It's cool. Okay. Now, if we add 50 plus 150, okay. Previously, we took into consideration our resolution. The resolution, it was always 0.1. So we multiplied by 10, saying that we have 10 values between each two whole values. But now our resolution is 2, meaning that each 2 values is represented by 1. So in this case we will divide by 2. Okay, because we skip a value. We say 1, 3, 5, 7, 9, 11, so on and so forth. Okay, but Previously, we were just like 1.1, 1.2, 1.3, 1.4. So the total number here, if we did not divide by 2, it's going to be 200. But no. We have a resolution of 2, so we will be having 100 actual values to be represented, not 200, right? Full. So, but we need to add the 1 which represents the 0, right? So we will have total of 101 values. Okay, cool. And the number of bits, as I said in a couple of seconds, is 7. We did log base 2, 1 equals 7. Maybe it's not a whole 7, so we did an approximation. The type of the signal is still unsigned, as previously mentioned in the question. And our offset here, do you think we have an offset? Yeah, we have an offset. Why? Because we don't start at 0. The engine running was 0 or 1, right? The vehicle speed was 0 and the maximum was 300. But here in the oil temperature, we start at -50. So whatever value we have, let us say it's 1, no man, we will have it by -50. So our offset is -50. Okay, so what we did in this question, we just setting up the characteristics of 3 signals. The engine running, again, I will do it very fast here just to recall every single thing that we understood from this question. The engine running is this signal, just it's saying either the engine is running or not. So it's black or white, it's 0 or 1, right? Okay, do we have a resolution? Yeah, we have a resolution of 1. Our step size from this value to this value is 1, right? Cool. Okay, going further, this is the physical value section. This is the actual physical value of the signal. So we need to digitize this physical value into digital value in order to understand it and encode it and do whatever we want with it. So now what is the total number of values that we have? We have either we count our minimum and the maximum. 0, 1, 1, 2, right? So the total number of values here is 2. Okay, and the number of bits to represent it, so log 2 base 2 equal 1. So the number of bits is 1. Our type is unsigned, as previously mentioned. Still unsigned. The type of the 3 is unsigned. So we go to the offset. Do we start somewhere other than 0? No. So our offset here is 0. Do we have a factor? Yes. The factor again is the disguise name or the fancy name of resolution. When it says resolution, so we are talking about the physical value. If we are talking about the factor, so it is the digital value. Okay. So the factor is the resolution, which is 1 in our case. Okay. Cool. The vehicle speed, as mentioned before, we have a resolution of 0.1 kilometer per hour. But that's it. So vehicle speed 0 and the maximum as it's in the solution is 300. So and it is mentioned in the question the resolution is 0.1. Okay, cool, that's perfect. So our total number of values will be 300 times this resolution is 10, because between each two whole numbers we have 10 steps. So it's going to be 300 3000 plus the value of the 0, so it's going to be 3001. Okay, and the number of bits log 2 3001 is 12. So the number of bits is 12. Still no change, it's unsigned. The type of the signal is unsigned. And then our offset, we don't have any offset because we start at 0 still. Okay, and our resolution here is the factor here, so it is 0.1. So wrapping up this question, this long question, we converted the physical values into digital values to be understood by our MCU. Going to the second part of the tutorial, which is concerned with the CAN bus. We will not re-explain what the doctor explained in the lectures because we will talk about very small things. But in a nutshell, the CAN bus is like the I2C bus, but it's more used in cars. It's for data transmission. Okay, same old, it's just related to cars. So question number 1 in the CAN bus part, we have screenshots. Okay, 2 screenshots. We need to give all the characteristics of the CAN message. On the right, this is the CAN message. And number B, it says how much space is left for additional signals without changing the DLC field. The DLC field is the data length code. Okay, first of all, this is the message characteristics. So number A, the characteristics are the name of the signal, which is, let's say it's the name, the ABS data, okay, this is the first characteristic. And number 2, it has an ID, right? This is the message ID 0xC9, this is the ID, and we have the DLC or the data length code 6. This is 6 bytes. Okay, so 6 times 8, we will have the total number of bits in the DLC, which will be 48 bits. Okay, so number A, the characteristics of the CAN message. It has a name of ABS data, the ID is 0xC9, and the data length code is 6 bytes. Converting it into bits, we have 48 bits worth of space to save data in. Okay, inside the message itself, we will be having, it has 4 signals. The car speed, as you can see here, this is the car speed. We have the gear lock. Let me just okay, we have the car speed, we have the gear lock, we have diagnostics and acceleration force. Okay, we have four signals within this message. Okay, and we have the length of each message in bytes, in bits. This concerning the second part of the question, which says how much space is left for additional signals. Okay, so we will add up these bits. Again, this message, it has total of 4 signals. It contains data about 4 signals, which are the car speed, which has 10 bits in length, and the gear lock, which has a length of 1 bit, and diagnostics, it has 8 bits. It consists of 8 bits, and the last one is acceleration force, is 16 bits in length. So if we add them up all, it will be 35 bits in this message, but the DLC is 48. Okay, so we have 13. If we come here and we can say left bits, the left bits to use are the 35 of our 4 of our four signals minus the total number of bits. Okay, yeah, is 48, but I will okay, 48. You will have total of 13 bits to use. Okay, but you put this in here and this in here in order not to get a negative, so I just like put it first. Okay, so again, the characteristics of the CAN message as in the screenshot: its name, its ID, and the DLC. Okay, this message contains 4 signals. Each signal has a different length in bits. Okay, so the second question asks whether we can put more bits or not. Yes, sorry, more signals or not, without changing the DLC field, without increasing the DLC field. Yeah, we can do that because 48 minus 35, the 35 is the total number of bits occupied by the 4 signals, 35. So 48 total number of bits in DLC minus the 35 is 13 bits. So we can add signals as long as they are 13 bits or less. Okay, that's question number 3. Now we will solve question number 4, the last question in this tutorial. Okay, we have 3 nodes: node 1, node 2, and node 3, and we have the resulting bus signal, and each node carries information and wants to be the one which transmits its data, but we only can have one node at a time. So at the start of frame we have 11 bits until we reach the remote transmission request. So in between we have a resulting bus signal, one of the 3 nodes, by the knowing that 0 is dominant and 1 is recessive, meaning that the 3 nodes, they will transmit all together at the same time. But if we have, let's say, node 1 and node 2, they have 1, and node 3 has 0 at the same bit, node 3 will win, not node 1 or 2, because 0 is more dominant, or not more, it's dominant, and 1 is recessive. Okay, so we have here the start of frame 1 1, and you can see here 1 1 1 1 1 1. At 8 we have 0 0 and 0, so it is 0. Let me just have vertical lines in order not to go out, because it's two novas. Okay, so that's really simple. So simply here we just want one node to win the arbitration. Okay, and this node will go and be the transmission. Okay, cool. So let's say node 1 is 0 0 0, node 1 2 node 3 from 9 to 8 is 0, so 0. We also here we have 0 here. What? Okay. we have 0 here, 0 and 0. Okay, node 1 0, again node 1 is still 0, right? Node 2 is 1 now. Node 3 is 0. So 1 1 and 0, 0 0 and 1. Node 2 lost the arbitration and it is out until this round is finished. Okay, until one of them wins the arbitration and gets transmitted, and then we will go back and try with node 2 again. Okay, so node 2 is out, we will left with node 1 and node 3. So 1 1 0 0 1 1 0 0, we are okay. 1 1 0 0 1 0 0. Okay, so 1 3 zeros, 1 3 zeros, same. 1 3 zeros, 1 2 3, again 1 1 2 and 3, and 1 and 1 again, we go 1 and we go 1 again, 1 and 1. Node 1 continues to be 1, but node 3 goes to be 0. So at bit 1, node 1 lost the arbitration, and node 1 is the one will be transmitted. So the resulting bus signal is of node 3, so it is 0 0 1 0 1 0 1. Okay, so here at bit number 1, node 0 lost the arbitration, and at bit 7, node 2 lost the arbitration, and the one which will be transmitted is node 3. Okay, because again we had here at bit number 7, node 1 was 0, node 3 was 0, node 1 was 1, and 0 and 1, 0 is the dominant one here, 0 is the dominant one, so 1 is recessive, so it got kicked out, and node 1 and node 3 kept going together until node 1 lost the arbitration at bit number 1, and node 3 is the first node to get transmitted on the CAN bus. After that, we will go back, node 1 and 2 will play together and see who will get out with a new version of, not a new version, with new values of node 3. Okay, thank you so much for listening to this tutorial. Best of luck, and that's it. Thank you so much.